So we've gotten our answer, and it's equal to delta of x minus y. And if you remember, we studied this function a few videos ago. And one of the things that I demonstrated to you about this function is that it is in fact Lorentz invariant. Now, I want to remind you of something else. So we also calculated, remember when we built our single particle theory, we calculated a probability amplitude. And when we calculated that probability amplitude, this was the probability for the particle to move from y to x. And the answer that we got for that probability amplitude is, it was an integral d3k over 2 pi cubed. So this looks very similar to the above. But then we had an e to the I k dot x minus y. So what's missing is the 1 over 2 omega k, which appears inside our delta. So precisely this 1 over 2 omega k, that appears inside our Lorentz invariant amplitude, but not inside our probability amplitude. And in fact, that's what makes the Lorentz invariant amplitude Lorentz invariant. And the absence of that makes sure that our probability amplitude transforms as a probability amplitude should. But you can study this integral using very similar methods to what we used when we studied the probability amplitude. So that was the thing that I wanted to say. And the conclusion of that study is the following. You will learn that delta of x minus y is not 0 when x and y are space-like separated. And what's another way to say that x and y are space-like separated? Well, you shouldn't even blink. It's when x minus y squared is less than 0. And by that x minus y squared, what do I mean? I mean x minus y mu contracted with x minus y mu. Oh, these are all equivalent ways to say it. So what that means is, in our new field theory, particles can still move faster than light. Okay, so let's discuss this now and try to figure out if this is okay or not. Now, before we do that, I just want to talk a little bit more about delta of x minus y. And what I want to do is I want to remind you of something that I think that you will know from quantum mechanics, okay? So imagine that we were studying quantum mechanics for a particle in a potential like this, okay? So this is the x-axis. And if the particle has some negative energy, so it's got an energy less than naught, then it's bound, it's trapped inside this potential. But what does the wave function psi of x look like? And I'm sure you solved this problem in your quantum mechanics course. And one of the things that I think you'll remember is inside the well, the wave function oscillated. And when you left the well, the wave function became exponentially damped. Okay, so I've drawn on psi of x here. This was x, and this axis over here is psi of x. And what you see in this central region over here, okay, what would we call the central region? Well, we would call it the classically allowed region. And in this classically allowed region, psi of x oscillates. Okay, it behaves just like a wave that is oscillating. We also have these regions at the edge here So this green region over here, and this green region over here, and these regions are classically forbidden. Okay? If you were a classical particle, you couldn't reach into these regions. You can only reach in there because of quantum mechanics. But in these regions, the wave function has these exponential tails. And so the wave function is exponentially damped. Okay, that's how psi of x behaves. Psi of x is exponentially damped. Now, why am I mentioning this? Well, if we look at the behavior of delta x minus y, so delta of x minus y oscillates if x and y are time-like separated. So just the kind of behavior that you had when you were in the classically allowed region, time-like separated. And in fact, delta x minus y is exponentially damped if x and y are space-like separated. So if they're space-like separated and you increase the separation between them, this delta x minus y decays exponentially. Okay, so just to make sure that you know what I'm saying here, let's say that x mu is 0, x. Let's say that y mu is 0, y. So this is certainly space-like separated. Then the way that delta of x minus y behaves, it does something like this: e to the minus the mod of x minus y times by the mass. And in units where c is equal to h bar is equal to 1, that exponent is dimensionless. And what you can see is as we increase x and y, delta of x minus y goes exponentially past to 0. Okay, so that's the behavior of delta x minus y. Now, the natural question to ask is, if I measure phi of x, why doesn't this disturb phi of y when x and y are space-like separated, so when x minus y squared is less than 0, since particles can move faster than light. So this is the basic question that I have to come to terms with. If I measure phi of x, why doesn't this disturb phi of y, even when x and y are space-like separated, since particles can move faster than light? And for this description, we are going to need the concept of an antiparticle. So let me explain what we are going to need. Now, when we study antiparticles, it is actually necessary that we talk about charge. Now, we've studied a real field. To study a field for a charged particle, it turns out you need to study a complex field, and we haven't done that so far. Okay, but that's okay. I'm going to talk about charge anyway, and just to put across the idea, but bear in mind that we're studying a field associated to a neutral particle because our field is real. To get a charged particle, you'd need to study a complex field. But I'm going to study the charge in the universe as a function of time t, and I'm going to imagine the following situation. I am going to create an electron, so I'm going to study electrons at time t1, and I will destroy it at time t2. Okay, So that's what I'm going to do. So let's put on T1 and T2 in this plot. So here is T1 and here is T2. What does the charge in the universe look like? Well, it'll look something like this. So we start off with a charge of 0, let's say. Then I create an electron. So what will happen? The charge of the electron, the charge of the universe will now become negative, and it will be a charge of minus E, the charge of 1 electron. So when I create an electron, I've created a charge of minus E, so the charge of the universe went down. Then I keep going at this charge, it remains a constant, until time t2, when I destroy the electron. When I destroy the electron, I get rid of a charge minus E from the universe, and I go back to a charge of 0. So this drop over here will happen whenever I create an electron, and this jump up over here will happen whenever I destroy an electron. Good. Okay, now I want to consider a different situation. I want to say, let's create, okay, this is going to sound weird, but let me do it. We're going to create an electron at time t2, and we will destroy it at time t1. So the reason why this sounds weird is I'm going to destroy the electron before I've created it, okay? But just let me do it and let's see what happens. Now we have a charge which is 0 up until the time t1. Now at the time t1, I destroy an electron. And take a look at the plot. We said when we destroy an electron, the charge goes up by an amount, E. Why? Because destroying an electron removes minus E from the universe. So we're going to jump up here because we destroyed an electron. Then we keep propagating at this fixed charge. Oh, let me be true to my scale. Now we keep propagating at this charge until time t2, and at time t2, I create the electron. And when I create the electron, the charge always goes down because creating an electron adds a charge of minus E to the universe. So here I created an electron. And this is, of course, E. So what does it look like? When I create the electron, and at some later time I destroy it, it looks like a particle propagating with a charge of minus E. When I destroy the electron before I've created it, it also looks like a particle propagating, but now the particle has a charge of plus E and not a charge of minus E. So in fact, this plus E, that's called a positron. It's the antiparticle of an electron. And one way of thinking about the antiparticle, the positron, is that it is an electron traveling backwards in time. When you actually study the Feynman path integral, you could study the world line of a particle, and the particle is allowed to move forward in time, backward in time, forward in time again. So the world line is allowed to flip backwards in time. And when it does move backwards in time, the interpretation is that it is an antiparticle. So the message that I wanted to get across to you is that conceptually, we can think of antiparticles as simply the particle which is moving backwards in time. We'll continue in a moment.